Good morning, gentlemen and Hannah. Good to have you here today. We're going to be going into another application of calculus, integral calculus, called disk method for volume. And so now we've been working up till now with the two dimension, the area under a curve, area between a curve, and so we're taking this disk method is sort of a logical extension of that, because it's like taking an area under the curve and rotating it about an axis. And so that's what we're going to do, create volume.
3D.
So 3D, yeah, so it's a 3D application. So it's the first time we're getting into that. And so what you have for this is the formula here, part 50. And what this is this, when you say R, you're talking about R squared. R is what is like an outer radius. So we take that radius of the curve and rotate it. And so that's where we get our pi r squared. And we're given a little step process here to figure out what to do, and that consists of drawing a region to figure out sort of what's going on. We find the limits or bounds of integration. We find the radius, r, to set up the integral, and then we use our formula here to integrate. And so our limits would be a and b, our r would be our radius, and that's it. So it's really, other than that, a very simple problem to do. So if we look at our first example right here, which is this one right here, the region enclosed about the x-axis, the line x equals 3 and the curve y equals square root of x is rotated about the x-axis. What is the volume of the solid generated? And then they're given a little, without a calculator. By the way, a lot of these types of problems tend to be with calculator problems. So for that, it'll be a matter of setting it up. So what will be the first step on this thing here? If you look at the steps, so draw it, right? So we're going to draw this. And it helps sometimes, I don't know how good you are at your artistry, but it can help sometimes to do a little bit of a 3D drawing if you can. Yeah, so we'll kind of see what it looks like. So you remember what the square root function looks like?
Yes.
Yeah, so it's going to curve something like this, right? And then we're going to be the x-axis, the line x equals 3. So here we have y is equal to square root of x. That's this equation. So we're talking about this boundary right here. And then if we 3D it, we can kind of look at it like this, right? If we're sort of looking at it from the end, we would see kind of an oval looking shape, wouldn't we? If we looked at it. Well, it's not going to look exactly like that. Let me go ahead and I want to kind of get rid of this here. Let's do this. So which way are we rotating? Rotate about the x-axis. So we're rotating it about the x-axis. So the thing is going to rotate down in this direction like this. And now what we're talking about is a shape like this. And so now I'm drawing kind of an oval. So here's looking at it sort of from the edge. And so we're talking about this volume right here. So what is this going to be roughly the shape of? What does this kind of look like?
I don't know what you call that.
That has a point at the end?
Like a cone.
It could be like a cone, like a round cone. I'm thinking kind of like a bullet almost.
Bullet. Oh, I didn't know we were doing trick questions.
Trick question? No, it looks kind of like a bullet, right? So we're looking at that, and so we see, if we look at it, I try to draw it this way. The bullet is going to be flat at this end, and then it's going to gradually curve to a point here, more or less a point here at the origin. So that's what the thing is going to look like. And so what is the integration of that going to be? How do we integrate that? First of all, what are our volume? What are going to be our limits of integration?
0.
0 to 3. And one thing I like to do whenever I do this, one of the very first things I do is I put this outside. I put a pi right outside here. And then it's going to be R what? R what's going to be the area of a circle? Pi R squared. So we take our R, which is right like this, and we're going to square it, and then dx it right like this. And I'll tell you from my experience, the easiest thing, the thing that I forget the most when I do these is what? What do you think I forget when I do this?
Oh, you got it.
I'll tell you what it is since you didn't know. I forget pi.
Oh.
I forget to put the pi in there because I start working on it. I says, okay, I square this. I get direct. So now we have this. We can simplify this. So I get v is equal to pi 0 to 3. What we have is x dx. Okay? Does that make sense? We square the square root. Boom. That's what we have here. So we go ahead and integrate this. What are we going to get when we integrate this? Pi, and the integral of x is
X
squared over 2, and we're going to evaluate between 0 and 3. And so what we have here is 3 squared, 9 over 2. So we're going to get 9 halves pi, and then we could subtract out 0 times all that, which is going to be 0. So we're really looking at that. 9 halves pi is our answer to that. Okay, that's it. And really, logically, all that we do, all the ones that we do are going to be similarly simple, I would say. Okay, you have any questions about this? All right, what we're going to do now is look at the next example. And let me erase these here. And you might say hi to Kylie today. Kylie might be watching, or she should be.
Kylie.
Hi, Kylie. Now, here we have another example. Find the volume of the solid generated by revolving x equals 1 plus y with y equals 3 and x equals 0 about the y-axis. So then there's a tweak, with or without a calculator. I'll tell you what I like to do on these things here. One trick I do if I'm uncomfortable with using the y-axis, I just change everything to x. I change everything y equals 1 plus x with x equals 3 and x equals 0 about the x-axis. So you can do that. So I want you to work on this one. We'll go over here in 4 to 5 minutes. Yes. Yes, I really did say that. So now, what you have here is you can do it, this one, if you have x equals square root of 1 plus y, what that's going to look like, something like this. That's what it's going to look like with y equals 3. So y equals 3 and x equals 0 about the y-axis. So it'll be like this looking thing here. All right, so you're rotating it. And so this is going to be another what?
Bullet.
It'll be another bullet. Okay. Now here, what you have is what are your limits of integration going to be? Looks like -1 to 3. One thing, when you realize what something is, one liberty you can take also is you can, if you decide to shift the thing up, you can kind of change your axes and make this instead, like let's say we move our axis down here like this. Well, if we do that, what are we going to have instead? We'll have 0 to 4. So sometimes you're able to kind of simplify your arithmetic a little bit depending on what you see. So you can do that. So if we do that, I'm going to keep with the -1 to 3 anyway. So we have, what is our volume going to be? It's going to be pi. And we're going to have -1 to 3, and we're going to have square root of 1 plus y squared dy. Does that look right? This is calculator with calculator, without a calculator. What we have here is v is equal to, we're going to have pi, we have -1 to 3, we have 1 plus y here, dy, so that's going to give us pi times, what is that going to be? Y plus y squared over 2. And we're going from -1 to 3. And now we can just start plugging in here. Our answer is going to be 3 plus, we're going to have that 9/2 again, right? And then we're going to subtract out this thing here. Subtract out, we'll have -1 plus -1 squared over 2, and that's going to be pi times everything, right? So really from here on out it's a matter of arithmetic, because here we have -1/2, -1 plus 1/2, so that's going to be like plus 1/2, So we have pi times 3 plus 9/2 plus 1/2. So I'm looking at 5, maybe that's going to be like 5 plus 3, so 8 pi. Does that look about right? Let's check this in the calculator, make sure it's right. Let me get let's get our calculator out. So it's going to be like 25 or so, it should be. Worked out in the calculator. Maybe, maybe not. So first thing, pi. The thing that I forget often. In math, 9, -1 to 3, and we have square root of 1 minus x. Or it's 1 plus x, isn't it? Is it 1 plus x or 1? It's 1 plus x, isn't it? Is it 1 plus x or 1 minus x? 1 plus x. And we're going to square that. Well, here I'll do it this way. Let me do it this way. I'll just put parentheses 1 plus. Delete. So I'll put 1 plus x like this, and then dx. So, yeah, so does that seem like that's going to be 8 pi there?
Try dividing it by pi.
Divided by
See if
pi?
you get 80.
Okay, divide by pi. Yeah, I think it's probably good. Looks good to me.
That's a big word.
Yeah. So that's right. Okay, so there's really, that's really all there is to it. Did you do it with the x? Did you change it to x and do it with x?
I did.
You did? What did you do? Hannah? Carson, what did you do?
I didn't get that.
Okay, where did you get stuck on this deal?
After the fourth step.
So here?
After the fourth step.
Down here? So you were okay up to here?
Yeah.
Kind of, okay. So really, what you're talking about here, after this part, this is all simplification and fractions. That's all that is. Right. That's all simplification and fractions. That's all that part is. So 90% of what's important for you, or maybe even more, is to get this far. If you get this far, all this other stuff is details. And if you get this far, what do you have? You have a calculator problem, don't you? Okay, so if you set it up right, you got a calculator problem, and you got the same answer that we got by simplifying on down here. Okay, that's it. So that's really note card, pretty much note card 50. And then it brings us to, let me see where the next one is here. We get to note card 51, which is washer method. Okay, do you know what a washer is?
Yes.
Yeah. It's something that's mechanical, it's something like,
It can also be used as a spacer.
pardon me?
Well, a different kind of washer used as a spacer.
Yeah, so what you're doing here, you're talking about a washer, you're talking about two curves like this. And what you're doing is you're taking this two curves and you're rotating this space between the two curves about an axis. In this case, we revolve about the x-axis. It's going to come like this, but it's going to be solid all around. And so from the side, as this thing rotates, it's going to be really sort of a hollowed out like a pot or something like that, right? A hollowed out pot at a point, because this thing is going to rotate around, and so from the side, this will be solid appearing.
Hey, Bishop Road.
And then we look at here, we would see kind of an oval here looking in there. It looks kind of like an eye, yes.
So so back whenever this would have been like last year,
Uh-huh.
whenever I went to the academy, I
Yeah.
went through one of the calculus classes, this is kind of what they started getting into, just like a little more complex. And like one of the kids in there he basically was like saying it was almost like a CAT scan, kind of how it takes like 3D imaging, like almost like a CAT scan, really,
Yeah.
kind of how he compared it. That's
Yeah.
a little interesting take.
So one of the students noticed that? Yeah, that's right. It is kind of like that, because that's what CAT scans do, right? They rotate to get a 3D image. They rotate around something to get a 3D image. Yeah, that's what they do. And so there is another extension of this called the shell method that has another level of complexity, but in our course, we're going to get this far. And so really, it's the same as the disk method, except you have this big R, as we call an outer radius, and this little r is called the inner radius. And so like the inner radius would be like the equation of this graph here, and the outer radius would be this one up here. And then you go ahead and put them in there, but otherwise it's the same situation. Now these are where a very common mistake, besides forgetting the pi, what's another common mistake that I've made or that's easy to make on this one?
You mix up the big and little R's.
Exactly. You mix up the big and little r's, and that has happened to me maybe too many times for me to count. But how do I know that I've made a mistake when I work it out?
We negative.
Yeah, I'll have a negative answer. And if I find that that is the case, I will go back and fix it by doing what? I'll go like this. And that'll fix it. Yeah, that'll fix it. Just absolute valutize it by doing that. So that's a trick on that one. So let's go ahead and look at, and again, a lot of these things end up really going right to the calculator when you look at it. Okay, here we have, in fact, a calculator problem. So I want you to look at this one here and do this one. And I'll come back to you. I'll tell you one thing, that when you sketch it, well, I'll have you sketch it first, and then we'll talk about it, what it looks like. Hope you can sketch that. And yes, this is a calculator problem.
What shirt you got on today?
What's that?
What shirt do you have today?
What shirt? Oh, I'll show you. Yeah, I got the pre-calculated shirt. What happened is last year, this is sort of newly reminted this summer because I changed it. I had those numbers on the back, but I had the unit circle on front, and then on the back I have a little the hand trick thing where you can find sine and cosine and tangent with that. So that's what I have on the back.
Mr. Joe, you could do, if you wanted to, after you're done teaching, you open up like a clothing website and sell those shirts.
Yeah, well, that's a good idea, but I have my T-shirt manufacturer is actually working on that. What he's doing is he makes these T-shirts that I do, and he's working on a website that's going to be my own website. It's going to be like a sub-website on his, where I can order, and then it will go right to their business, so they can print out. So it'll be commercial like that, so it's going to combine our two enterprises together.
You can advertise it on your YouTube channel too.
Yeah, we can. Now, the thing that YouTube creators are allowed to do is they have little Teespring shirts, shirt stores on their channels. If you see the channels, you've seen those, right? On YouTube channels. The thing about it is I'm not qualified for that level because I don't have enough subscribers.
How many?
I need to have 10,000 subscribers to do that.
How many do you have?
I have like 2,300 or 2,400, something like
Well,
that.
more than that.
That's what I have, but that's okay.
Still impressive.
It's not bad. But really, it's all, the channel is 2/3, 60%, 2/3 of my traffic is based on Slope Dude. But that's okay. Slope Dude is
How many views does Slope Dude have?
about 500,000.
That's crazy.
Yeah, it's kind of, but the thing about it is, when it comes to YouTube, you never know what's going to be popular. Like
One video just might blow up for like absolutely no reason.
well, like when I started doing my first YouTube channel, I did a calculator program for using the quadratic formula to find the roots with the quadratic formula. And before I knew, that video had over 100,000
I was
views.
about to say, if you're looking to get like viewers, start doing guides on how to program different things for your calculator.
Yeah.
Like just step by step, and that'll definitely get a bunch of views.
Yeah, I do. I do a lot of those on the calculator, and those are some of my most popular ones when it comes to that. Yeah, you're right about that. And the thing about it is, for the way I did it was with scope. Anyway, let's go ahead here and look at this. So we have y equals x squared. So we have y equals x squared, and the line y equals 4. So here's y equals 4. And we have y equals x squared. So what are going to be our limits of integration? Well, before we do that, we're talking about this thing right here, and where are we rotating it? We're rotating it like this, right? So thing's going to come down like this, and looking off the side, it's going to be like this. We're going to see this thing rotated, but it'll be like a shape. So it'll be like narrowly connected right here at the origin. So what's going to be our limits of integration for this? What are the intersection points here? So yeah, we have -2, 4 here, and we have 2, 4 here. So what we should have is, our volume should be this times the integral from -2 to 2 of what's our outer radius? What's big R? What's our outer radius here?
Y equals 4.
Yeah, so y equals 4. So we have 4. So we have this is big R. So 4 equals big R. So what big R squared minus, what's this thing going to be here? What's little r going to be? So we have x squared squared. So we can just make that x to the 4th, right? And then we are dx. And then we put that in our calculator. And what is our volume going to be for this guy? We have pi. We have mass -2. There's another thing you can do that's a trick on this. I'll tell you what it is in a minute. Because there are really some, now, with a calculator, it really doesn't matter. But we have like 16 minus x to the 4th dx. Is anything being forgotten here? Anything forgotten here? I can't think of anything.
Yeah, pi.
Pi's right here, yeah. No, I'm glad you mentioned it, because that's easy to forget. So get this, I want to show you another trick, and this trick is really helpful, not where you have a calculator. Let's say you didn't have a calculator for this. What you can do is you can say, well, you're looking at this, and you're saying, well, the volume of this, you have symmetry here, so your volume is going to be twice this. So instead of doing it this way, what you can do is this. You can go 2 pi. It's kind of a way of checking your work too. 2 pi, and then math 9. Instead of going -2 to 2, we can just go 0 to 2. And we should get the same thing if we have perfect symmetry here, right? Minus x to the 4th. And we have dx, there we go. It should be the same. Is it the same? Yes, it is. So 168.850. And we look up here, last thing to do is look for units. I don't see any units given, so we don't have to add that. Are you always looking for units when you do your problem? Should be looking for units, okay? And then this is it. So this is probably where we start tomorrow, page 743, okay?